Good morning to our EMAG webinar participants. I am Rick Crema, EMAG Regional Sales Manager for Midwest USA. Our webinar today is Shaft Machining, why vertical turning centers are ideal for this topic. My colleagues, Alexander and Andreas, will present excellent information for you. So, Alex, take it away.
A warm welcome from our side, from Germany. My name is Alexander Neumeister. As head of engineering in the shaft technology, I'm responsible for customer projects. With me is Andreas Druffe, technology expert in shaft machining and our product manager.
Hello.
As in all live EMAG webinars, you have the opportunity to ask us questions. So please use the chat for an official question or the question tab on the right side for an anonymous question. We are happy to answer them if the question is for the topic we are talking about. If it's too specific, then we will appreciate to answer them later or contact you. But just go ahead, don't hesitate to ask your questions. They will, Rick, get these questions and send them directly to us. Let's get started. You basically know two machining strategies in turning shaft-shaped components, horizontal or vertically wise. EMAG opted clearly for the vertical system and the vertical strategy. From our point of view, they are the best and the most benefits for you as a customer in this machine concept. In the next 45 minutes, we would like to show you the advantages in using a vertical turning center from our VT machine series. In the beginning, Andreas will give you an insight to the machine technology and its wide range of applications. And in the second part, I will show you how versatile and efficiently these machines can be linked together. Now, I will give the floor to Andreas.
Thank you very much. So, welcome from my side. And I have four headlines what I want to show you about the VT machine series. First of all, we start with the machine structure and have a look for the working area and the footprint of the machines. Second would be the modular design, because these machines are construction kits. And you will see how we can configure our machines for the requirements of our customers. Third point is integration of different technologies. And last but not least, we want to have a short view on some examples, what we did in the past, so you see how the machine is working in real life. So first of all, machine structure. This video you see we have a main body with cast granite. Then we implement a spindle on the top side. It's a movable spindle in the vertical axis. The cable chain for the spindle. Tailstock on the bottom side, fixed. Some housing of the machine. The cross lights left and right. Now you see the turrets. Left and right housing. Cable chain. Now from the left and the right you see our standard automation. And the front doors. And you see the working space is good reachable for everything you have to do. In the back we have the energy container and the chip conveyor. And now we have an example with an injector body. The left turret is loading the part with a gripper. We do the end finishing of the injector body with a special tool. The drilling operations 2 times here. Now we support with the tailstock and do the rough and finish cutting with 4 axes. And now on the left side we have a tangential rolling head for rolling the thread. And after this, the right turret will come with its gripper and unload the part to the right side automation. Here we have a look on some values of the machine. On the right side you see our mostly common configuration. On the top side you will see the spindle, the movable spindle. At the bottom side you see a tailstock. In the background you see the slide for the steady rest, but there's no steady rest in there as you see, but doesn't matter. And on the left, on the right side, you see the turrets for tooling on turret 1 and 2. We are building the machines in 2 sizes. The smaller machine is a VT2 or VT 100, and it's designed for workpieces with a diameter up to 100 millimeters. And the bigger machine, the VT4 or the VT 200, is designed for workpieces up to 200 millimeters. The naming VT2 and VT4 shows us it's a machine with a FANUC control unit, and the VT 100 or VT 200 is in principle the same machine but with a Siemens control unit. The smaller machine is designed for chuck diameter 160 millimeter and the bigger one 250 millimeters. The part diameter, as said before, 100 or 200 millimeters. The maximum part length, depending on clamping device, is 400 millimeters or 630 millimeters. And the gripper on the both turrets are restricted at around about 100 millimeter or 125 millimeters. So if you have any recommendations, above these values, don't hesitate to ask us, and we have some solutions to increase these values in a smaller way. So we see the footprint of the machine. In this page you will see the VT2 or VT 100 with a standard automation and with a chip conveyor. In depth is 5.1 meter. For the VT4 we need 5.6 meters, roundabout. And the width is 2.4 meters, and for the bigger machine it's 3 meters. And the machine is 2.55 meters high. The bigger one is 2.9 meters high roundabout. And with a cable chain you've seen before, we use 3.4 meters in high and 4 meters for the bigger machine. So next will be the modular design of the machine and the machine configurations. In the picture you see we count from the left to the side, so track 1, 2 and 3, these are the vertical axes, and track 1 and 3 is also the same for the turrets, and in the middle you see the track for spindle, tailstock, steady rest. We equip our turrets with BMT 55 interface or BMT 65 interface. For the bigger machine 65, and each turret with 11 positions for tooling and 1 additional position for the gripper for loading and unloading. It's also possible to get the machine with VDI 30, smaller one, or the bigger machine with VDI 40. We can use all turrets with or without driven tools, and also with or without a y-axis. Track 2 in the middle, as you can see here, we have a spindle on top and a tailstock at the bottom. As I said, the spindle is movable, and another option is to use 2 spindles instead of a tailstock. So we have a spindle on top and a spindle at the bottom. And with this configuration, we, for example, can do 2 clamping situations, so op 10 and op 20 for a part with 2 parts at the same time in the machine. And each of the turrets can reach every spindle, and with this we can guarantee short cycle times. Another option is only a spindle at the bottom and a movable tailstop at the top. And this gives us some advantages for handling of the workpieces, especially while linked machines are in the plant and we have to do op 10 and op 20 in 2 machines, for example, and we don't have to swivel the part 180 degrees and go through the machines and it's ready. However, we have 2 exceptions. We have an additional machine called the VTC 200 CD. In this machine we don't have a steady rest, but it's not necessary because it's a machine for center drive. And another machine is a VTC 200 EE, what means it's an end machining machine. And for this we have on both sides turrets with each 5 spindles, and each spindle with a HSK 63 interface for rotating tools. And in the middle we use a movable clamping device with 2 adjustable clamping rows for different part lengths.
Andy, can I interrupt for a couple questions?
Yes.
What is the center distance of the VT machines?
Center distance from front of the tailstock to the spindle is 750 millimeters for the smaller machine. And for the VT4 or VT200, it's a little bit more than 800 millimeters, I guess 807. But we can increase the width between tailstock and spindle around about 160 millimeters if necessary.
Very good. What is the spindle power possible?
Spindle power for the smaller machine is maximum 27 kW, and for the bigger machine is 38 kW, roundabout.
Thank you.
You're welcome. So, next point will be the integration of technologies. Here we see some examples. First of all, we have a radio measuring probe on the turret, and with a single probe we use it normally for measuring the 0 point of the workpiece in the machine, or measuring length. And in this example here you see there is a fork on the radio measuring probe, and with this fork we can measure diameters with the y-axis. Next points, with driven tools we can engrave. Don't need driven tools for skiving, but we do skiving, or scroll-free turning. We will see some examples a little bit later. We can do normal drilling, milling operations. We can do gear hobbing or single tooth hobbing with live tools. We also can turning out of rounds, for example pistons, but the machine is a little bit different, and you can see here, but it's possible, and we did it sometimes before. And next is rolling tees or threads with tangential rolling head, for example. And some more ideas what you can do or what we do. It's not only an idea, we do it. Is brushing, sewing, everything what's needed.
Andreas, we have another question.
Yes.
How long does an operator take on average to change a tool?
Okay. So it's depending on how your operator is prepared for this. We think about around about 2.5 minutes, maybe 3 minutes for the first tool after stopping the machine, because you have to open the doors and so on. And for each additional tool in this machining stop, we count 1.5 minutes roundabout. And these are the values for us for calculation, the tooling change.
Thank you.
No problem. Okay, we go further with application examples. Here we see a worm shaft. The left turret is loading the part, measuring the 0 point with a radio measuring probe. After this, we do 4-axis turning on the upper side. You see we use a special shaft chuck with retractable jaws and a phase driver. You see it later. Now we use jaws for higher torque and can do the rough cutting with 4 axes on the bigger diameter and a little bit faster. Doing the 4-axis rough turning on the bottom side. And now we retract the jaws for a better runout and do finish cuts. Also 4 axis. And while the right turret now will finish the area for the helix, what we do later, the left turret gets his next tool on and is prepared for its operation. Right turret is ready, left turret will start operation, and the right turret is changing tool and turning the thread. Left turret is on start for skiving, or scroll free in this case. We use the jaws and do the milling operation, also with the y-axis. And now we're doing the helix with 4 axes and with the jaws. And now we retract the jaws and the left turret will finish the clamping seat to remove the clamping marks. And after this, the right turret will come with its gripper and unload the part to the right side. In this example, we do soft skiving. For shorter seats, we use only the y-axis, but there are restrictions in length of the skiving inserts. And for lengths like this here, you see we need also the z-axis additional to the y-axis, but we get a very good surface and we do finishing very fast. Here we have an example for skiving rotor package and finishing the upper side face. And now we come with 2 tools, so it's a rough turning with prime turn. is for access, and then the right turret will get the skiving tool to get a short cycle time and a good surface. In this example, we will see we do not only load and unload from the left to the right side, we are also able to load and unload from the right to the left side. And it's also possible to load and unload only on one side. Left or each doesn't matter. Left or right doesn't matter. So the right turret gets a part. Now you see the left turret is unloading the last part. The right turret is loading the part between the centers. And we start the operation. Left turret finishing a bearing seat, and a sealed seat is pre-turned for skiving. Left turret is unloading, right turret gets the next part, clamp between centers, and we're at the start again. And unloading with the left turret, and go to the automation. Now you can see an example a few weeks ago. We do gear hobbing with the live tool on the left turret, and shifting will be done with the y-axis. So you see it's also possible. Well, last but not least, we have an example with a special gripper on the right turret. This gripper is loading the part from the automation into the machine, and it's able to do the end machining. So the left turret comes with the live tool and doing the milling cut on the lower side and centering on the lower side. Now we go down and do the same on the upper side, and then end finishing is ready, and the part will be prepared for clamping between centers. Go down with the spindle, and we are ready for turning. So I hope you enjoyed. It was my pleasure to introduce you something about the machines, and I give the word back to Alex.
Thank you.
Thank you.
Andy, for your technological insights of the VT's machines. Let's move to the standard automation and interlinking options. In first step, I will show you some standard loading and unloading features, like you have already seen in the video, just now shown on the slide in addition. And afterwards, you will get an impression of how well VTC machines can be combined and linked together. So, overview of the machine from the front side. As you have seen, the biggest advantage of this machining concept is that the machine brings the automation already with itself. And to the left turret, it picks the raw part, and at the same time, the right turret picks the finished part from the spindle and put it on the conveyor, on the part storage conveyor. And this is made in simultaneously in the same time, which saves up to 8 seconds of waiting time instead of loading and unloading from only one side. In this state, the basic machine VT2 and VT4 are standalone machines, and without additional protective fences operates it. Let's take a closer look to the components, turret grippers, and workpiece storage options. On the left side, the loading gripper, it can be equipped with rigid or pendular jaws, depending on whether a raw forging contour or a pre-machined workpiece is to be loaded. They can always also be fitted with different inserts, for example, to protect sensitive surfaces from clamping marks after machining. In the middle, the vice gripper you already have seen. It is used for cutting to length and centering the workpiece, so it can be machined immediately between centers. On the right side, the steady rest gripper. Sometimes it is not possible to install a permanently steady rest in the machine due to interfering contours or, for example, long or protruding tools in the turrets. So this can be a helpful solution if you need a steady rest in the machine. Those three are the most common grippers from EMAG and in the VT series. For the workpiece storage, you have already seen on the left side the standard configuration with the through loading principle, left to right or right to left, and with the circular storage. Beside, it's the possibility with the L or I shuttle on the left side of the machine. The L shuttle goes through the back of the machine to the other side, in this case on the right side, where is an additional single loading position on point number 3. But the shuttle under point 2 can also be cutted as an I shuttle, and the track motion system can go through the automatic loading area in the back of the machine. On the right side, there's the possibility to install buffer conveyors. They can be suitable if the hard-linked machining with OP 10, 20, 30 have different cycle times, and so it can be a good combination for setup times. The other two machines are still running if one machine is getting new tools. Some additional options for the loading and unloading area. For example, we have swiveling devices or orientations on the pallets. In this case, you see the circular storage. The pallet itself has a pinion orientation because the shaft has the same inside. We have to swivel the workpiece so that the mandrel of the spindle is clamping the workpiece at the first touch and does not have to search it. Then optional on the raw part sides, where we can install height controls or type checks. If you produce several batches of a part family, so that it's a security check, not that the wrong raw parts are being loaded by the operator. Then we can read QR DMC codes, doing active position alignments, or on the finish side, additional measuring devices or writing units.
Excuse me, Alex.
Yes.
How many workpieces fit on the standard automation?
On the standard automation, we go back on the left side, they are fitting up to 27 workpieces. It depends on the weight of the workpieces. The VT2 machine can carry 125 kilograms. The VT4 can carry 250 kilograms. So the limit is either 27 or 27 pieces or 125, respectively 250 kilograms.
Thank you.
So now I will show you some examples of interlinkings. I will go from the smaller one, from production cell up one, and in this case I want to show you always the type of the workpiece storage and the loading. Here we have linked the machine and the robot cell with our SCS4 stacking cell. As you can see, we have only left on the machine, only a left side storage. And the cycle time allows it to make the left loading and unloading principle. The stacking cell itself is charged with an AGV. The cell itself has also a SPC or NOK drawer, and here you can see the chutes of the stacking cell. On the right hand side we have the loading position, then we have not full part baskets, raw part baskets, and on the left the finished part. Just for sum up. Another cell automation is in this case a VT 100, even with a roboter, and on the left hand side a grinding machine, G160, even from the EMAG. Here we do have a through loading system. What I've shown, a single loading position. The robot picks a raw part. In this case it's a hardened part, it's a finish machining cell. The turret picks the part, and the end machining at the finish machining is being done, grooving and skiving for the bearings. So pretty fast cycle time, so that the simultaneously loading has to be done and unloading. Here you see the L shuttle. The workpiece is provided to the robot and he picks it up and straight load the grinding machine. Afterwards, it's been deloaded from the grinding machine and stacked in the baskets again. So this was the L shuttle and single type position. And the third one, the third well-known, is the track motion. Still successful track motion system. In this case, it's a part of a production line. Customer provides the robots for loading and unloading. Here we do have two VT 200, even a rotor. In this case, a different one. The machines are being loaded by an ice shuttle from the back of the machine and unloaded on the other side. It's a through loading principle again. Both machines, both VTC machines, are doing the same job, the same operation, due to higher output. While the finish turning has been done on the first machine, the second machine will be loaded by the track motion. And measuring probe for 0 point setting, and if when the finish turning has been done, the track motion picks the rotor up It's going through a blowing up station and place it on a measuring and writing device. The finished part is going to the loading position for the customer robot to pick up. This for the track motion system. Yes, Rick.
Yes, excuse me for a question. Why an L shuttle when one-sided loading is also possible?
Okay, I think this question I hand over to you.
Yes. So, as we said before, the fastest way to load and unload the parts is through the machine, so from the left to the right or from the right to the left. But we're also able to load and unload on only one side, but this means we need a few more seconds. So for the L shuttle, we need round about additional 400 millimeters in the width of the machine. Could be sometimes a problem in the plant, but we use it to load through the machine to get reduced cycle times. But with this fast machine, maybe it's not possible to implement an L shuttle, and the cycle time is not the problem. So we don't have to use a L shuttle, and if you don't need it, you don't have to pay for it.
Thank you.
You're welcome.
Okay. Thanks. So let's get bigger. Here we do have a production line. In order to dispel the myth that the vertical machine concept can process bar material, I would like to present you a realized production line. On the left-hand side, number one, we do have the bar feeder. And in the end of it, there we have a saw. The saw cuts the bars into pieces. These pieces are rolling to the track motion system. The translift picks them up and turns them in a vertical position. So the VT 200 machines, op 10 for roughing, op 20 for finishing, can be loaded again vertically. The track motion transports the finished part from the turning into the gear hobbing HLC 150 machine, even a EMAG machine, and later to the cleaning station where the robot is picking the parts from into a measuring unit, a labeling device, and is stacking into baskets. The cycle time of the complete line is about 90 seconds. 90 seconds and in the length of the production line is 28 meters. Please imagine to use a horizontal lathe. In 90 seconds, you cannot rough and finish turn the workpiece. 90 seconds, so you need a second machine. A second horizontal machine needs a second bar loader. And the length of the complete production line is increasing more and more. So it's the most compact system you can get on the market. So how can we reach those good results in our complex product lines? We are not relying anymore on just our experience. We are relying now on professional plant simulation software to get the best results and the best optimal solution for you as our customer. We feed our machines and the complete line and units with real machine data. From your side, we need your workpiece, the raw and the finish condition, and in the end, your available floor space. We are calculating cycle times. We make setup time optimization, maybe it is a workpiece buffer necessary. We can reduce your standstill or your idle times. In the end, we do have an amount of spindles you need, and the best output you can get at the end of the day in the available space you have. So this is this is ongoing only in the offer phase. So afterwards it's not necessary anymore, but in the offer phase we make these simulations together with you in order to get the best solution. So, yeah, we're almost at the end of the presentation. I hope you understand why we are absolutely convinced of the vertical turning concept. In short, I will sum up the advantages on this slide. You have an unhindered chip flow. The chips are falling straight down in the chip conveyor. You have short processing types. You have 2 turrets which are making 4-axis machining at the same time. Short idle times due to simultaneously loading and unloading. You have an ergonomic, excellent accessibility to the working area. Favorable automation options. For instance, the basic configuration all brings the automation loading and unloading already with it. You have flexible automation capabilities. You can place a robot beside the machine without changing the design. We have a small footprint, especially in the wood. So you have, in the end, really compact and short production lines. They can be realized in a vast space-saving manner. And the easy link-up of several machines in a row due to a variety of automation options. So this is from our side the conclusion. I thank you in the name of Andreas too, and
Alex,
thank you for hearing. Rick, I give the word back to you.
we did have one more question come in.
Okay.
A participant wanted to know about if it's possible to balance the rotor in the machine, or if not, how do we verify runout?
The balancing is not being made in the machine itself, so we need additional balancing and measuring and balancing unit afterwards. But the runout is exactly the run between the spindle and the tailstock.
Okay, thank you.
If there's in
participants, did we get through the summary?
Sorry. Yeah, if there's an additional question to it, we will present you the contact of Andreas, where you can ask the question in a more detailed way if you want. Otherwise, place the question to Rick, and he will forward it to us. So, excuse me, it's your turn.
Well, on behalf of our participants, thank you, Alexander and Andreas, for that informative and detailed presentation. And as Andreas just stated, you can continue to submit your questions in detailed format to either myself or Alexander or Andreas. And thank you for participating today. Goodbye, and have a great rest of your week.
Okay, bye-bye.
Bye.